Whether you are lost in a foreign city or lost in the plethora of molecular interactions of a cell, you have to solve the same problem. How do I get from A to B, and what is the shortest path? And if one road is blocked, is there an alternative? Not to get lost in a labyrinth, Theseus had Ariadne's ball of a string. But what do we have? Computers? Already in the previous lecture we have used the terms network, pathway and path in a more or less intuitive, unthinking way. Before we continue, we should briefly try to come up with a couple of concise definitions.
Let's consider a network like this. You may remember from the first lesson that this is a directed graph. In such a network or graph, a path is a connection between two objects or nodes. The distance between these two nodes may be of any length. They may be direct neighbors or located at opposite ends of the whole network. Also, the path between two given nodes may be of any length. The one with the lowest number of connections or edges is called the shortest path. The term path can be used for biological networks, but it is also a term in graph theory of mathematics. When talking about biological networks, however, we are more often faced with the term pathway. Is it the same as a path? It is not. Pathway is a biological concept, not a graph theoretical one. But can we map it to what we call a graph? In biosciences, we talk, for instance, about the EGF pathway, the NF-kappa-B pathway, or the MAP kinase pathway. In none of these or similar cases we deal with a single linear path as we have just outlined. Rather, each of them has one particular node or eponymous one that is part of a number of such paths. Sometimes these pathways are not as exactly defined as it would be necessary for mathematical description, and the term is sometimes just intuitively used. In our simplified diagram, it may look like this. As you can see, there are many paths that start from node G. All end up in 5 different nodes. We might call them all together the G pathway. We mentioned one example, the EGF pathway, which is the collection of all paths that are triggered by epidermal growth factor EGF. Similar, when there is a number of paths that all end up in one node, like this one, here different paths that are triggered by 4 different objects converge at one node, here labeled V. In biology, we might call this the V pathway.
And finally, of course, when we want to address the entirety of all nodes, edges, paths and so on, we speak about the whole network, or here, the complete directed graph. Now let's have a look how we could tell the computer how our network looks like. That is, how many and which nodes are there and which of them are connected. For us, the graphical representation may be fine, unless the network becomes really big. But the computer needs something else, something more formal. There are 2 easy ways to describe a graph in a formal way. We call them adjacency list or adjacency matrix.
Let's have a look at an undirected graph like this. The adjacency list lists now for each node all its neighbors. For instance, node P is connected to nodes Q, R and S. The adjacency matrix gives you an overview of all connections in your graph by putting all nodes in rows and columns, and the cells of the matrix indicate whether 2 nodes are connected, labeled 1, or not, labeled 0. Here you can see in either row P or column P that node P is connected to nodes Q, R and S, but not to T and U. The diagonal contains only zeros, since there are no self-edges or self-loops. When we introduce such a self-edge, for instance, to node P, we see that P appears in its own adjacency, AP, and in the adjacency matrix, the PP connection turns into 1. But let's go back to the original graph without self-edge. You can see that the matrix is mirror symmetric when reflected at the diagonal. This is also intuitively clear, since when node P is connected to Q, Q has also to be connected with P. Remember, we deal with an undirected graph. So you may guess how things change when we move to a directed graph. The adjacency matrix is not symmetrical anymore. In this example, you can see row P from row P that node P points at node R exclusively. But it is pointed at by nodes Q and S, as indicated by column P.
We may now ask the question whether there is, for instance, a way to reach R from S, or whether there is a path from S to R. In biological terms, is there a way for an organism to produce substance R out of substance S, or is there a regulatory influence from S onto R? For that, we will use our adjacency matrix.
First, we confirm that there is no direct connection leading us from S to R. Instead, we can see that we can reach node P from S, as we see in row S, and next we switch in column P to row P, where we see that we can reach R from here. The total path length here is 2, which is the number of edges that we pass along this path. This is equivalent to the number of horizontal movements in our matrix. The number of connecting nodes that we pass is here 1, node P, which is equivalent to the number of vertical movements in our matrix. But row S also shows us that we can reach T from S, and row T instructs us to go to U. And from U we can reach R. You see, we have found a longer but alternative path which would still work if node P would be taken out of the graph, be damaged, disconnected, whatever. We can call this virtual knockout experiment, and there are more paths we could walk along from S to R.
Frequently it is of interest to find the shortest path between two nodes, not just any path. That is relevant for biological networks as well. A shorter path between, say, a membrane receptor and a nuclear transcription factor may be more plausible than a much longer one. If it physically exists, the longer path would be more prone for any kind of disturbances. If it is computationally inferred, more assumptions may have to be made. Think of Occam's razor. In the simplest case, the length of a path is, as we have seen, the number of edges between start and end node of a path. However, finding shortest paths becomes particularly relevant when your graph is a weighted one. That is, each edge is attributed a weight. If your graph, for instance, represents a map with cities as nodes and connecting roads of railroads as edges, the weights of the edges could simply be the distances. In a metabolic network, the weights could represent some biochemical parameter, maybe the kinetic constant of the reaction, or rather an inverse of it. There is one well-known and widely used algorithm to find shortest paths in a graph. It is the Dijkstra algorithm. And here you see the inventor of that algorithm.
Look at this very simple graph of 3 nodes and 3 edges. Don't be confused, it's 3 times the same. You see that the edges are weighted. The task is to find the shortest path from S to U That is the path with the lowest sum of weights, or say costs. Just by looking at it, you may have immediately recognized that the path from S to T to U is cheaper, we say shorter, than the direct one from S to U. And what you have done more or less automatically is what Dijkstra does. Starting from S, it costs us 4 to go to T and 10 to go to U. We assign these values to these nodes as kind of attribute. And we decide that we go cheapest from S to T. We take these two nodes for the next step. We know already that it costs 10 to go to U from S directly. But we see now that it takes us only 2 to reach U from T, what together with already paid 4 makes 6 for the whole path from S to T to U. When we compare, we see that 6 is lower than 10 and have found our shortest path from S to U. Although it needs to pass 2 edges instead of 1, it is shorter with regard to the sum of weights. That looks a bit trivial, doesn't it? You may wonder why to undertake such an effort, be it words or with words or computationally, for something that is obvious just by visual inspection. Well then, let's have a look at a slightly more complex task. In this graph of 8 nodes and 15 edges, we may wish to know the shortest path from node A to node G. We apply Dijkstra, and to anticipate this, the algorithm will give us all shortest paths from node A to any other node. Note, we put the symbol for the start node down here. For what purpose, you will see later. First, we check again which neighbors of A we can reach at all. B, E, and C. And what would be the weights or costs for each of these moves? We immediately see that it is cheapest to go to E. We put the symbol for E down here, connect it with A, and take now node E as an additional start node for the next step, keeping in mind that it has cost us 1, say, point to get there. In the next step, we check all neighbors of nodes A and E, which are B, F, and C. We add the weight of each of these connections to the costs we had to reach the corresponding start node, which is 0 for A, the original start node, but 1 for E. Compare all costs that we come up with, 28, 9, 27, and 2, and take the lowest. This is 2 to go from A to C. We add C down here, also connected to A. C enters our collection of start nodes now. The neighbors to our now 3 start nodes, A, E, and C, are still B and F, plus H. We compute again the costs that we have when we go to each of these neighbors from each of the connected start nodes, plus the costs we had to go to the respective start node. You see that the cheapest path now is the one leading us from E to node B. B becomes another start node, which is also added down here, connected with node E. What you also see is that the costly edge from A to B, 28 points, is now out of the running. It will never become part of any shortest path starting from A. The neighbors of A, B, E, and C are now D, F, via 3 different connections, and H. We again compute the costs to reach each of them from each connected start node and see that it is cheapest to go from B to D. Node D is added now to our diagram. At the bottom it is picked as an additional start node for the next round. We will repeat the procedure with our new set of start nodes and noticed that the next cheapest step is to go from B to F for altogether 19 points. We could have reached also F from E or C, but either path would be more expensive. Going to either G or H would be more costly at this step. We do the same again and again until all nodes, G as the last one, are connected by a shortest path to our original start node, A. Now you also see the purpose of our diagram at the bottom. It instructs us how to reach any node of the graph by a shortest path starting from A. We call this a minimum spanning tree. We would have to repeat the whole procedure when choosing another node as the original start point.
There are other algorithms. Some of them simultaneously compute all shortest paths in a graph at once, like the so-called Floyd algorithm. But for now we'll stop here and we'll show an application example in another video. But the next one of this series will deal with a different topic of graph theory. How can we describe and analyze the characteristic features of a given network? For instance, what does it mean when we say we are living in a small world? See you next time.